So let's start with just an overview where we are, because we passed 3 weeks, we met last time 3 weeks ago. So let me go here in the tutorials, and what we discussed 3 weeks ago was just a premise, the learning process, and a premise on the structure of beaches, berms, and bars, shoaling, waves. Okay? Last year I dedicated one lecture to the mechanics of sea waves. As I told you, given that this is overlapping with what Professor Archetti does, I decided to skip it. So I put anyway available to you the page that I prepared last year, because I wanted to make clear what I may ask you at the exam. And if you see differences between what is reported in this page and what Professor Archetti did, it's not a problem. You can reply to my question with whatever version you want. So you may look at this page to see what is my interpretation. You may look to, you may reply with the words of Professor Archetti. It's absolutely not a problem. Let me clarify what are the questions. And if you see something that it's not familiar to you, just let me know, okay? So the first question is how to derive the Laplace equation, which is this one. And I think you did it with Professor Archetti. And basically what you have to do is to start from the continuity equation and introduce the assumption that the fluid, the motion, is the velocity field is irrotational, and therefore you can express the velocity as the derivative of the velocity potential. You substitute here and you get Laplace equation. So I think, again, if you see something that is not familiar to you, like what is this? We didn't do it with Professor Archetti, tell me, okay? And then if you also, this equation to be integrated, need some boundary conditions. So this is the bottom boundary condition. The sea bottom is not permeable, and therefore the velocity in the z direction is null. And the boundary condition at the sea surface. Okay. There is also this dynamic boundary condition. Usually I don't ask it. So what it is just enough for me, more than enough, if you provide a textual reply, not this relationship. So if you say the boundary condition are at the sea bottom, and the boundary condition is that the velocity, the sea bottom is not permeable, and then there are two boundary conditions at the sea surface, which is the fact that the pressure is coincident with atmospheric pressure, and the fact that a particle fluid that is at the surface remains at the surface. You don't need to write it down, and this is fine. And another thing that I can ask you is how do you introduce the linear assumption? And you tell me what Professor Archetti told you, because I'm sure that you spent a lot of time on linear wave theory with Professor Archetti. So again, my question is, how do you introduce the linear assumption? At what stage? And if you say something more and you write down the relationship, of course it's fine. And you can write down the relationships that you learned with Professor Archetti. What I just want to let you know is that I may ask this question, mechanics of sea waves, because of course it's important, and I know that you did it. So you are supposed to know it, because it is, you took the exam, I think, in January or later. I'm not sure when. Okay, then what is dispersion? Okay, you know, these wave properties, I don't ask them. I think it is extremely interesting, this table. And it refers to the linear theory, and it tells you what is group velocity, what is dynamic pressure, what is whatever. But I don't ask it, I don't need it. So this table is just there for your knowledge. Also, phase velocity is something that usually I don't ask. And that's it. So, mechanics of seaways, I propose to skip it. If you have any question, again, please don't hesitate to ask me. Then, this is the lecture, the descriptive lecture that I wanted to introduce last Wednesday. I think it is, even this one is overlapping what you did with Professor Archetti. This is classification of beach protection measures. I want them to be clear to you. I think it will be already. So I don't think it is harming if you skip it. Basically, I say that there are active and passive measures. Active measures, I'm sure that you know them. It's breakwater, groins, beach nourishment, also called beach replenishment, and sand bypass. Sand bypass maybe that you don't know, so let's spend a couple of words. The beach nourishment, it's, okay, I'll tell you a couple of words. So, and the passive measures include seawalls and revetments. Revetments is like this coverage of the berm that you see here, and berm protections. Okay, seawalls, you know, I think with Professor Kitty you studied what they are. Breakwaters. Breakwaters may have protected breaks. In this case, look at the legend. The submerged structures are in dashed lines. So what you see here, these are blocks of concrete that are sometimes used to protect the breaks among the breakwaters. Not always used, sometimes they are used. It's also possible to couple groins with breakwaters. It is possible. And in this case, the breakwaters are submerged with weak submergence, while the groins are emerging. And when the breakwater is submerged, usually they put signals, emerging signals, to avoid the boats crash against the breakwaters. These are groins. They may be just simple groins or T-groins. Groins, they are spelled in different ways in the American English and UK English. I think the spelling here is UK English, but I'm not sure. And the alternative spelling is with the I and not the Y, I think. And the plural is probably without the E. Anyway, it's a small, and this is a small island. Beach replenishment is basically, I'm not sure if you discussed it with Professor Archetti, you put sand on the beach. The problem of putting sand on the beach is that if you don't do anything else, then the beach is taken away by the currents. The replenishment is removed by the currents, because of course, if you need to put replenishment of sand, it means that you have erosion in that location, and you continue to have erosion even if you put sand. So basically it is removed. This is why replenishments are very often coupled with groins or breakwaters, submerged or not. Replenishment is useful because it accelerates the beach recovery. And also, if it's done in a continuous way, indeed, you may completely replace with nourishment, replenishment, you may completely replace hard structures like breakwater and groins. So basically, after an estimate of the sediment transport, you estimate what is the volume of sand that you need to bring usually during the winter on the beach, and if you repeat the process every year, this is something that can avoid hard or black interventions. There are still some environmental impacts associated to replenishment, because think about the living ecosystem in the sand, which is there. Of course, if you put 1 meter of sand above the ecosystem, and the sand that you put there, typically it's a dead sand because it was excavated and then transported. Of course, there is an impact on the ecosystem and the vegetation. Also, there is an impact because of the diameter of the sand that you use. Usually we tend to use a sand with an increased diameter to replenish, because we want to prevent erosion. and therefore we use a higher diameter for the sand, and it's visible. You notice that. You notice the difference between the original sand and the replenished sand, and it's not very good for the recreational activities, if you notice the intervention. So today there is some engineers believe that it's better to try to replenish with a sand that looks very similar to the original one, but this is not always possible, because of course any sand is unique. So if you get the sand somewhere else, it's different in colors, diameter. Anyway, this is a kind of environmental impact that should be considered. Okay, and then here there is a discussion on the groins, what are the groins, and that's it. And I wanted to make the structure first because, as I told you, I want to start with a discussion on the structures and then focus on their design. But in this case, I think that almost everything that I'm discussing here, you know it. And I'm not sure if sand bypassing is explained here. Let me see. I don't think so, so we can skip it. We can skip it for, okay, sand bypass, but it's described later in a lecture that we still have to do. So we can discuss it extensively now. Okay, so if you agree, now I pass to the topic of today, which is beach hydrodynamics and morphodynamics. And also I have a PowerPoint presentation on that. You can also call it coastal hydrodynamics and morphodynamics. So what is this subject? Basically, coastal hydrodynamics studies the movement, the motion of seawater close to the coast, and therefore takes care about currents, waves, etc. And this is the reason why it's called hydrodynamics. Keep in mind that a dynamical system is a system evolving in time, and hydrodynamical system is a dynamical system dealing with water. In this case, it's seawater. And it's, when we talk about hydrodynamics, given that we refer to a system that is moving in time, we are talking about moving water. And of course, hydrodynamics can refer to rivers, can refer to the sea, to the ocean, etc., and even in some cases to lakes. In this case, we are referring to coasts, and the movement of water is, can be generated by waves and currents. Okay, what is then morphodynamics? Morphodynamics is the study of a dynamical system that deals with morphology, and in particular with morphology, in this case of beaches and coasts, and therefore it deals with erosion and accretion, erosion and deposition, erosion and siltation. We can use this term more or less as synonyms. Accretion means the fact that a beach is accreting, so is increasing in size. Erosion means that a beach is decreasing in size. Deposition means deposition of sediment on the sea bottom, and the deposition of siltation means the same thing. So we are talking about movement of sediments, and in particular in beaches, movement of sand. Sediments may also be coarser than sand. They can be gravel, and also morphodynamics deals with long-term erosion. What refers to the movement of sand generally refers to short-term processes, erosion and accretion, typically intra-annual or seasonal processes. What deals with erosion of rocks, rocky coasts, is something that refers to longer scale processes. Beach and coastal morphodynamics deals with everything of that. When we talk about beach morphodynamics, usually we refer to the movement of sand, and this is the kind of processes we will refer to. So we are not interested in the long-term evolution of coasts, which involves also tectonics and subsidence, or subsidence, probably it's subsidence, the pronunciation. What we are interested in here is the movement of sand. So we have to study the movement of water and the associated movement of sand. Keep in mind that the movement of sand takes place close to the coast. So this is not an offshore process. There is, at a certain distance from the coast, there is a limiting distance where you don't have transport of sand anymore. And this is also your experience if you go to the sea and start walking. Of course, at a certain point, the deep of the ocean becomes higher and higher. But if you look down, you don't see sand anymore. You start seeing less and less sand, and then you start seeing rocks. And this, if you go in the Adriatic Sea, is impossible because you have to walk up to the other coast in order to not to see sand, because it's very sandy. But if you go on the Mediterranean Sea, even if you go on beaches, there are beaches also in the Mediterranean Sea, you see that the sand finishes very, very close to the coast. So this is the movement of sand and beach hydrodynamics. It's something that is related to, it's an inshore process, it's not an offshore process. Okay, so you understand that we have to study the movement of water, and therefore we have to study waves. Given that we are interested we are more interested in the movement of waves than the movement of currents, but also we have to take into account currents if they are important. If we look at the situation, the context in Italy, and in particular on the Adriatic Sea, we are not much concerned by currents because they are not very strong. But there are in other, especially in the coasts, in the ocean, there are places where currents are extremely important, and therefore you have to study also the currents if you are interested in morphodynamics, not only the waves. And of course you have to get this information through the means that probably Professor Archetti introduced to you. You need observations. We will talk about sea monitoring. But in any case, beware that there are institutions that are in charge of taking observation of waves and currents. So if you need any information like is this a coast where currents are important, you need to refer to these institutions, and usually each country has its own institution. You have to refer to these institutions and find the data that you need. Okay, so I think I already talked about this. You know this video, and I think I don't need to introduce anything to you. Let's remember what is wave amplitude and wave height. And for a regular wave, you know that the wave height is twice the wave amplitude. Okay? And we usually refer not only to a regular wave, but also to a plane wave. A plane wave means that if you have waves traveling along a direction, so there is a velocity vector, and you cross the wave with a plane that is perpendicular to the velocity vector. This crossing plane, if you take it after a while, you get another plane. These planes are all parallel planes. So the wave is not turning, is not bending. Okay, this is the plane wave. The velocity vector is straight, it doesn't change its direction. And we refer usually to plane waves because this is an approximation that we can easily take without important consequences. And also we refer to the linear theory. Beware that the linear theory and the assumption of plane waves, there are some beaches where they are weak. They provide you only a rough approximation. And therefore, in these beaches that are very complicated, maybe that you need to use something that is more refined than the linear theory and the assumption of plane waves. So for instance, we are used to assume that there is a dominant wave direction. There are some beaches where there is no dominant wave direction. And also there are beaches where if you take observation, usually in modern times, we take observations with cameras about waves. And you see that there is not a dominant direction, even at a fixed time. Even if you take a snapshot, you don't see a dominant wave direction. You see several waves that are colliding each other, generating a very complicated velocity field for each particle fluid, which is a 3D field. So beware of this. There are beaches that are easy, there are beaches where the linear assumption or the assumption of plane wave or dominant wave direction is not really the best. Anyway, this is the nomenclature which refer it. And I don't spend time about wave forcing, and I think please confirm to me that you learned already how to estimate and design wave height, wavelength, wave period, extreme value theory. Did you already discuss about it? Oh, yeah, okay, so you know already the Gaussian distribution, etc. Okay, and I will recall them later on anyway. There is a lecture where I'm recalling the Gaussian distribution and the stochastic of waves. Okay, I think we can move forward. And so here, these are the features we refer with: wave direction, wave period, wavelength, wave amplitude. Okay, and now let's talk about sediment transport. This should be new to you. A premise. You see that I'm trying to avoid overlaps because I think it is very bothering to see overlaps in an integrated course. So I'm trying really this year to make an effort to avoid overlaps. But if you miss something, you have to let me know, because of course I discuss with Professor Archetti, but I'm not attending her lectures. So if you see something that is not clear to you, or if there is something that for some reason you prefer to be repeated, no problem at all. You have to tell me. Okay, no problem at all. And for whatever reason, maybe that you didn't attend the lecture, so it was your responsibility. Maybe that Professor Archetti had a code that day was not clear, no problem. I mean, any professor, any student may have some days where we don't perform well. And the same applies, of course, to everybody, including, of course, myself. So, if for some reason, again, you want something to be repeated, just let me know. Okay. So, now let's talk about sediment transport. Sediment transport is the driver of beach morphodynamics, beach morphology. So we have to understand it. But sediment transport is a very complicated process, both in rivers and even more in the ocean, in the sea. It's a complicated process because you understand that it's driven by motion of fluid, which is already difficult to study and to predict and to simulate. And then there is an additional process, which is the fact that the moving fluid has energy. This energy moves sediments and displaces them. So when the energy of the fluid is relevant, sediments are taken from the sea bottom and suspended into the wave. When the energy dissipates, then the fluid doesn't have enough energy to transport the sediment, and the sediments collapse and go over the bottom and stay there until some fluid particles with high energy come back and bring them in suspension. So this is very complicated. And the one thing that you have to understand is that this is a process that has a random component, meaning that there is a component of this process that cannot be described with a deterministic model. This is something that we need to take into account. Like for waves, what is the reason why we use a probability distribution, the Gaussian distribution, to describe waves? The reason is very simple, is that we cannot write an analytical relationship providing wave height, the expected wave height for a given record period. Because were we able to write this analytical relationship, it would be easier. We wouldn't need to take statistics into play. The problem is that we cannot write this deterministic relationship. And what is the reason why we cannot write it? Because we know these processes, we know the law of physics. If you think about movement of water, it's laws of physics. If you think about sediments that are suspended and transported, it's physics. We know these laws. So, what is the reason why we cannot write a precise model, a deterministic model, that gives to me an estimate of wave height, etc.? Keep in mind, the deterministic model is a model that establishes a one-to-one relationship. So there are inputs, observations. Deterministic model gives me a precise value. A probability distribution is not like that. It gives an expected value with some uncertainty. Okay, so what is the reason why we cannot describe movement of waves and sediments? There might be several reasons, but let me just introduce one. We cannot describe precisely the geometry of the system. This is very understandable. So, think about the sediments. We cannot know, we cannot describe the geometry of every single grain of sand. So if the grain of sand is bigger, of course, waves need more energy to suspend it. If we wanted to describe this process in detail, we would need to describe in detail the geometry. It's not possible. This is just one very understandable reason. There are other reasons why we cannot describe a process that basically we know, but cannot describe precisely. But let's forget about the other reasons. And let's now, and you may have heard about chaos. Chaos, if you go to Wikipedia, there is a nice description of what is chaos. The movement of sediment is chaotic. And chaos is that even if you know the deterministic relationship, a small change in the initial condition, a small change in the boundary condition gives to a completely different, leads to a completely different output. And the paradox of chaos, the very famous paradox of chaos, is the butterfly effect. You know the butterfly effect, which means that if a butterfly flies in Japan, then an hurricane is generated in the United States. This is a chaotic effect. It means a small perturbation of initial condition gives to a completely different, leads to a completely different output. But let's forget about it. But this is I wanted to mention it because it's a very interesting, I think it's a very interesting note. The presence of chaos can lead to a completely different and unexpected output. Because it gives rise to uncertainty. And so you can understand also in politics or the economy, when we talk about a chaotic system, this is the meaning that we want to convey. So an unpredictable system. Okay, when there is uncertainty and when there is difficulties, when you cannot use a deterministic model, the alternative solution is the statistical model. And this is why Professor Archetti introduced to you the Gamble distribution for estimating extreme wave height. Keep in mind, statistical model, you may say also a stochastic model. They are more or less synonyms. They are not rightly synonyms, but they are more or less synonyms. You don't have to be concerned by the word stochastic. It means statistics, basically. And beware of the fact, and this is something that is not known in general, statistics doesn't mean that you don't understand. It just means that you cannot describe deterministically something. And this is something that you have to be careful of, because when you talk about when you talk with your stakeholders and you use deterministic models, they are in general happier and happier with respect to using a statistical model, because they associate typically the person in the street, the public, associate statistics to uncertainty, lack of understanding. The first association is correct. We use statistics when there is uncertainty. The second association is plain wrong. Okay? Uncertainty doesn't necessarily mean lack of understanding. As I said, accounting system, we understand it perfectly, but we are just uncertain about the output. Okay, so, sediment transport. We can distinguish between cross-shore and along-shore sediment transport. It's clear. Cross-shore means that the sediment is perpendicular to the shoreline in both ways. Along-shore means that the transport of sediment is parallel to the coastline. We have a coastline. This is the cross-shore direction. This is the along-shore. We deal with these processes individually, meaning that we first consider along-shore sediment transport, and then we consider the cross-shore. Of course, if you have waves that arrive with an angle that is different from 90 or 0 degrees with respect to the beach, and usually we use this angle in order to identify the wave direction. Usually we identify the breaker line, which is perpendicular for a plane wave. It's perpendicular to the velocity vector of the wave, and we use the acute angle between the breaker line and the shoreline to identify the incidence, the angle of incidence of waves. I use it, and maybe that Professor Racchetti used the other one. It doesn't make any difference. It's just a matter of convening which angle we use, agreeing on which angle we use. And so if this angle is different from 0 and 90, of course, an incoming wave generates both processes, cross-shore and along-shore sediment transport. As I said, we focus on along-shore one first, and our question is how to estimate the magnitude of sediment transport. I already said it's a complicated process. It's a process with uncertainty, which means that, of course, the model that we use may have a physical basis, but should also include something empirical to take into account uncertainty. Okay. How do we measure sediment transport? You can measure it in volume of sediments per year. This is the typical unit that is used. Let me see, I have a table here. Just 1 second. Here. This is a table giving, just as an example, long-shore transport rates from US coasts, and this is in cubic meter per year. It's interesting to see the order of magnitude. What is the reason why I included this table in my pages? The reason is that I just want you to be aware of the order of magnitude. This is, of course, it can change a lot between coasts, and it can change in particular when you pass from the ocean to an internal sea. Of course, there is a difference. So if you want to have an idea, I don't have an order of magnitude to give to you for the Adriatic coast. I have to look for it, but it would be interesting to provide also an order of magnitude for the Adriatic coast. But it's also there is an order of magnitude here for the Gulf of Mexico and Great Lakes, which they are internal lakes, but they are very huge, so they are comparable to seas. So they have waves, they have important waves. And this is a possible way of estimating the sediment transport, which is volume per year. Another, you can use other units, and in particular, sometimes we use the weight per year of sediment per year, or immersed weight, which is the same thing, because you know the difference, but even if you don't know it, we will discuss it soon. Yeah?
Just to understand the real volume, like is that volume enough to remove a beach or create a beach in 1 year?
It depends on the beach, on the type of beach, but in general, I would say that in general, as an erosion process, unless there is a catastrophic event, it's not enough to remove a beach in 1 year, because there is a reason why a beach is there, and the reason is that there is an equilibrium that has been established in the long term. And then this equilibrium is corrupted by human intervention, but usually the human intervention is not as such as to destroy completely a beach in 1 year. The human intervention usually is the fact that we tend to limit the sand, the incoming sand from rivers, or maybe that we modify the currents in some way, and I give you an example soon. And if we modify the currents in some way, okay, you see the effect maybe in a few years, but in the range of just 1 year, it's difficult. But even in natural conditions, it may happen that you get a catastrophic event, like an event of those which happen on average once in 100 years. And in this case, you can get the beach completely removed. And it may take like 10 years to be restored naturally. And then you have to intervene in order to bring sand or something like that. So